Hi, I'm going to talk about this section in the notes about prism power. From lab, you played around with prisms and you found that fundamentally what prisms do is bend the light. And so as we show in this figure here, right, we have light ray coming in and it hits the prism and the light is deviated by some angle d, and that's the deviation angle. And something else that you saw in lab is you measured the deviation angle for your prism, and you found that these angles are pretty small, especially for the thin prisms that we're likely to be using in optometry. And so you probably found that deviation angles were around 4 or 5 degrees, 6 degrees, and that turned out to be like tenths of radians. So, that remember that means we have to grapple a little bit with these two different ways of measuring angle. So we can measure angle in degrees, which you're probably pretty familiar with, and then also radians, which probably is not quite so familiar. And one thing to just sort of get a practical handle on that is a radian is actually a pretty big angle. So like if you have a circle, we know that this full circle is 360 degrees. And a radian is about this big. It's 1 radian is about 57 degrees, right? It's pretty big. And so as you saw in lab, the angles, the deviation angles that we deal with are much smaller than that. They're, again, a few degrees. They're tenths of radians. And so it's inconvenient if we're forced to measure them in radians, as you'll see we are. We need to measure these things in radians, or at least it's convenient to. Quoting the numbers in radians would be really cumbersome because it would be like 0.01 or 0.03, and that's inconvenient. And so what we do is instead of using radians, we use a different unit. We use cent_rads, right? And so there's 100 cent_rads in 1 radian. So it's just a smaller measure of angle. It's sort of like centimeters are to meters, right? There's 100 centimeters in a meter. And the reason for having cent_rads is because the deviation angles that you experience with thin prisms are pretty small. And so it makes sense to measure them in hundredths of radians, or cent_rads. You also saw in lab that you could put a screen and like this figure shows, measure the deflection y of the light ray that has traveled through the prism. So you place the screen at some distance x and you measured what the y value was. And I'm just going to sketch that over here. Okay, so I've sketched this scenario with the prism. We have a light ray coming in. It's deviated by some angle d. And then you go and place a screen some distance x away from the prism. Right, and you can measure the deflection on the screen, some value y. And one of the things you also did was you noticed that if you place the screen at a different location, then you will have to measure a bigger y, but the deviation angle hasn't changed any. So that's just, as you go farther and farther away, the deflection on a screen gets bigger and bigger. And in fact, it's in proportion, right? So this y value is in proportion to this x value. The bigger the x, the farther away the screen is, the bigger the y value goes. And in fact, we can even see that from trigonometry. We know that if I look at this triangle right here, right, the tangent of that angle, so the tangent of d, is opposite over adjacent, which would be y over x. So what y and x are telling us is actually the tangent of the angle. And that's a constant, right? For one particular prism, the light ray comes in, is deviated by an angle d. That's the same angle all as the ray travels everywhere. And so the tangent of that has to be the same. And so this ratio has to be the same. And so, again, you saw that in lab. So just sort of an interesting sort of mathematical thing is if we happen to set x to 100 centimeters and measure what our y is, just looking at this equation up here, we can rearrange this to say, okay, so y would have to equal x tan d, and if I've made x be 100 centimeters, right, I would do this, and that's interesting because we actually define the power of a prism. We define the power of a prism as this z quantity is 100 times tangent of the deviation angle. And so why do we do that? Well, I mean, number one, most importantly, the prism power is something related to the deviation angle, and that's what matters, right? Because deviation is what a prism does. And again, why is it 100? The 100's there because the angles are small, and so we want this prism power to be some number that's 1, 10, 15, not 0.01. So notice that if we happen to put the screen 100 centimeters away, then this stuff here is all exactly what we call the prism power. And so we would have a situation where the prism power is equal to the deflection on the screen y measured in centimeters, right? When x equals 100 centimeters or 1 meter. So that's really handy. That gives us a really practical way of understanding. If someone tells us, oh, here's a prism with a prism power of 16, what that means is that if you put a screen 100 centimeters away, 1 meter away, it will deflect the ray 16 centimeters. Y would be equal to 16, right? Y is equal to z. And because of this proportion, right, because the deviation angle is constant, there's sort of this proportionality between y and x. If x was 2 meters, if it was twice as far, well, y will be twice as big. And if x was half as far, if it was only 50 centimeters, then y would be half as big, right? And so that all leads us to this big statement down here in bold, right? That what z is telling us is the distance in centimeters that an image is displaced on the screen for every meter that that screen is away from the prism, right? So just numerically, the numerical value of the prism power is the same as the numerical value of y measured in centimeters. And so that's just a nice way, I mean, so, right? So again, so you can interpret the prism power as telling you something about how much the light ray is going to be deflected in traveling a meter. And if you need to know how far it's deflected for different distances, then you just use this proportionality to figure that out. Now, for small angles, we know that the tangent of an angle is approximately equal to the angle itself, as long as we measure everything in radians. And as we sort of just got done saying, right, the deviation angle is usually fairly small, especially for thin prisms, which are the prisms we're likely to encounter. And so that's usually a fair approximation. And so that means we can sort of simplify things a little bit. We have that z is 100 tan d, but in a small angle situation, we can just write that as 100 times d. Again, d is measured in radians. And if d is in radians and we multiply it by 100, we've just converted that value into centrads. So I can also write this as d measured in centrads is numerically equal to the prism power. Right? And so again, that's also just a really nice way to interpret what the prism power means. If someone again hands you a prism and says, "Oh, this is a prism, has a prism power of 16," then that's telling you that the deviation angle is about 16 centrads, or that it will deflect the beam 16 centimeters on a screen 1 meter away. All right, so that just gives us some really handy ways of interpreting what prism power does, and also this really emphasizes how the prism power is directly connected to the thing that matters, which is the deviation angle. That's what a prism does, is deviate the light. So notice, a little bit unfortunate, I guess, that we do have now a whole variety of equations that relate the prism power to different quantities. And so just maybe worth collecting these all together. So the fundamental definition is the prism power is 100 times the tangent of d, where d is measured in radians. We can also relate the prism power to the deflection on a screen measured in centimeters, right, at x equals 1 meter. So that's a way to sort of interpret what prism power means, or relate it to a physical measurement. And in fact, since tangent of d is equal to y over x, we can also write the prism power as 100 times y over x. And the only thing to worry about there is that the y and the x values would need to be measured in the same unit so that the units cancel and we get a reasonable result over there. Then, if we're working with small angles, where we can use the small angle approximation, we have that the z is approximately equal to 100 times d, because tangent d is just d. Again, that would be d measured in radians. And in the small angle approximation, d is approximately equal to y over x, which basically leads to the same result as we have up above, just another way of sort of calculating it. And then finally, we can say that z is related to d if you measure d in centirads. All right, so variety of ways of working with the prism power, and it's sort of handy to know each of them and sort of where to use them. Now, what happens if you combine prisms and put them together? So basically, their effect combines. So the prism power of the combination of prisms is just the sum of the prism powers of the individual prisms. So I thought I would do this example that's in the in-class notes. So we're given two thin prisms made of a certain kind of glass, and we're given the apex angles. What is the prism power of the combination if their base directions are the same? So what we're talking about is we're going to have a prism, and we're going to add it to another prism, right? And we're sort of wondering, if I put light through this, what does it do, right? It has some overall deviation angle, which is somehow related to the total prism power of the combination. All right, and the rule says is we just add prism powers. So our first job here is to calculate the prism powers of the individual prisms here. So we're told that they have apex angles of 6 degrees and 4 degrees. So these are thin prisms. All right, so we can go ahead and calculate the prism power for each one of these things. And since they're thin prisms, we can use our thin prism result for relating the deviation angle to the apex angle. So remember, that's this expression here that says that the deviation angle is equal to n minus 1 times the apex angle. So I'm going to use that to calculate the individual deviation angles of each of these prisms. So call it d1, and it's 1.523 minus 1 times an apex angle of 6 degrees. And d2 is going to be 1.523 minus 1 times 4 degrees. Okay, so that gives us this results for the deviation angles in degrees, but I would like to have them in centirads so that I can relate them directly to the prism power. So now I'm going to convert these into centirads. So for example, d1 is 3.1 degrees, and then to convert into radians, I'm going to multiply by 2 pi and divide by 360 degrees, and then to convert it to centirads, I will multiply by 100. And similarly for d2. Okay, so I've converted these values into centirads, and I get the figures here. And so now the reason for doing that is, remember, for thin prisms, for small angles and small angle approximation, the deviation angle in centirads is equal to the prism power, or at least approximately equal. So once I have the prism powers, once I know the prism powers, then to find the total power, I just add them together, right? So the total prism power of their combination is z1 plus z2, and so that's just going to be the 5.48 plus the 3.65, and that gets me. So I find this result that the total prism power is 9.13, and that would be prism diopters. So it's this little funny symbol here with the prism triangle in it. So 9.13 prism diopters. All right, now what if the prisms aren't both in the same orientation? In this example we just did, both prisms, I had them with base down, so they're both deviating the light in the same direction. But the second part of the question asks, what if the first prism is base up and the second prism is base down? So base up and then base down, like that. So now they're not both trying to deviate the light in the same direction, right? They're sort of opposing each other, and so the total prism power is going to be sort of the difference between their individual powers. And to help keep track of that, just mathematically, I'm going to call one of these directions positive and one negative. So I'm just going to arbitrarily call this one, this is the base up, I'm going to call that positive, and this is base down, I'm going to call that negative. You could make any choice you want, it doesn't really matter, as long as we're consistent. So the total power is going to be positive Z1 minus the value of Z2. So that's going to be 5.48 minus 3.65. So that is a value of positive 1.83. Again, that's prism diopters. And what the positive is telling us is that the overall combination of these two prisms is acting like a positive, which in my choice of signs meant base up. So this is like an overall base up prism with a total power of 1.8 prism diopters.